Hey everyone, and welcome! If you've ever looked at integral calculus and thought it was the final boss of math, I'm here to tell you it's not. Seriously, think of it more like unlocking a new level and with it a whole new set of super powerful skills. Today we're going to build your personal integration toolkit piece by piece. So let's grab that first tool and figure out what integration actually is.
So think about it. You've probably spent a ton of time learning how to find the derivative of something, right? The rate of change. But what if you wanted to go backwards? What if you already knew the rate of change and you wanted to figure out what the original function was? That one simple question, that's the key that unlocks everything we're about to do.
And the answer to that question? Well, that's exactly what integration is. It's finding the antiderivative. You know how subtraction undoes addition and division undoes multiplication? Well, integration is the official undo button for differentiation. And today, we're going to learn exactly how to press it.
So here's the game plan. We're going to start with that core concept, the whole reverse of differentiation idea. Then we'll start building our basic toolkit with the must-have rules. After that, we'll add some specialized tools for trig functions, learn how to handle some of the trickier problems, and finally, we'll unleash the ultimate power tool, integration by parts.
Okay, first things first. Let's really hammer this core idea home. Every single integration rule we're going to learn, every single one, comes from this one simple fact. We are just reversing the process of finding a derivative. If you can keep that in the back of your mind, everything else is going to click right into place, I promise.
And check this out. This is the perfect example, the function e to the x. We all know its derivative is, well, it's just e to the x. It's its own derivative. So if integration is just the reverse, what do you think the integral of e to the x is? Yep, you got it. It's also e to the x. This shows that perfect, beautiful circle. It's our undo button in action, in the simplest way possible.
All right, we've got the main idea down. Now it's time to actually start building that toolkit. These next few rules are your bread and butter. They're the ones you're going to be reaching for 90% of the time. This is the foundation for everything else we do.
And this right here, this is the absolute workhorse of your toolkit. It's the power rule. Basically, if you're integrating any variable, let's say x, raised to a power n, you just add 1 to that power and then divide by the new power. It's the exact opposite of the derivative rule where you used to multiply and then subtract 1. This is tool number 1, and trust me, it's a huge one.
Let's see it in action, okay? Look at problem 21 here. We need the integral of the quantity x plus 1 squared. Now, you could try some complex technique, but here's the secret. Simplify it first. Just expand it out into 3 simple terms. And now look at that. We can just use our new power rule on each little piece one by one. The whole strategy is to break down a big, scary problem into small, easy ones.
Now this slide is super important. It's all about pattern recognition. On the left, you see some basic integrals, like 1 over x. Simple enough. But now look to the right. See that one? It's f prime of x over f of x. It looks more complicated, like something that came from the chain rule, but the pattern is identical. Once you know the integral of 1 over x is the natural log of x, you automatically know the integral of f prime over f is the natural log of f of x. Spotting these patterns is a massive shortcut. Okay, our basic toolkit is starting to look pretty good. Now, let's add some specialized tools. These are for a group of functions you're going to see all the time, trigonometric functions. And the logic is exactly what we've been saying. If you know the derivative, you just have to run it in reverse to find the integral.
And here they are. Whoa, okay, that might look like a lot to memorize, right? But don't sweat it. Just go back to our main idea. You already know the derivative of sine is cosine. So, what's the integral of cosine got to be? It's got to be sine. The derivative of cosine is negative sine, so the integral of sine has to be negative cosine. See? Every single rule on this page is just one of your old derivative rules in disguise.
Now, let's put these new tools to work. Take a look at problem 57. At first, that looks like a real mess. But if you look closely, you might spot a familiar trig identity hiding in there. That whole expression, 2 sine of 2x cosine of 2x, can be simplified way down to just sine of 4x. And by making that one simple swap, we turned a really nasty-looking problem into a basic one we can solve in a second.
So we've got our core tools, and we've got our trig specialists. But what happens when you run into a problem that just doesn't seem to fit any of our rules? Well, this is where I tell you a little secret. Sometimes the hardest part of a calculus problem isn't the calculus at all. It's the algebra you have to do before you can even get started. Take a look at this beast from problem 18. Trying to integrate that fraction just as it is? It seems impossible.
But if we use a little bit of old-school polynomial long division, we can rewrite that whole messy thing as a simple polynomial, x squared plus x plus 8, and a little leftover piece. Now, each of those terms is something we can integrate easily with our basic tools. The hard part was the algebra, not the calculus.
Here's another set of specialized tools for these tricky problems, the inverse trig rules. And these are all about matching patterns. The moment you see an integral with something like a square root and a difference of squares, like 1 over the square root of a squared minus x squared, a little alarm should go off in your head that says, hey, that looks like an inverse sign. These are like very specific keys for very specific locks.
Let's see that pattern matching in action with problem 67. If you look at it, it doesn't quite fit our inverse sign rule, at least not at first. But the key is realizing we can use algebra to rearrange it, to force it into that exact a squared minus x squared pattern that we're looking for. Once we've made our problem match the lock, our special inverse sign key works perfectly.
And now, it's time for the final tool in our kit. This is the power tool. This is the one you bring out when nothing else is working, especially when you need to integrate a product of two totally different kinds of functions. This, my friends, is integration by parts.
Here it is, the magic formula. The integral of u dv equals u times v minus the integral of v du. Now, what on earth does that mean? It means we're making a trade. We take one really hard integral, our original problem, and we swap it for a different one that is hopefully much, much easier to solve. The entire strategy is about making a smart trade.
Now that formula might look a little intimidating, but it's really just a simple four-step process. Step 1, you look at your integral and you strategically pick one part to be your u and the rest to be your dv. Step 2, you just differentiate u to get du. Step 3, you integrate dv to find v. And for the final step, you just plug all four of those pieces back into the big formula. That's it.
Let's see the payoff. Look at this problem, the integral of x times the natural log of x. None of our other tools can touch this thing. But with integration by parts, we can choose our u, find our dv, find all the pieces, and plug them in. And look what happens. We trade our original hard problem for the integral of 1/2 x dx, which is incredibly easy. And just like that, a problem that seemed impossible is now solved.
And there you have it. Your starter toolkit is complete. You've got the power rule for all the basics, the specialized trig rules, you know the crucial strategy of simplifying first, and you've got the heavy-duty power tool, integration by parts, for the really tough jobs. You are officially equipped to solve a massive range of integrals.
So the only real question left is this. Integration isn't just about symbols on a page. It's about finding areas, calculating volumes, and understanding how things accumulate over time. So now that you have the toolkit, what are you going to build with it? What problems are you going to solve?